Protostar. Every star begins here, inside a vast cloud of gas and dust drifting through space. When part of that cloud grows dense enough, gravity pulls it inward, and the material begins to collapse and heat up. At the center, a hot, glowing core forms and starts to spin, gathering more mass as it goes. It is not yet a true star because the core has not become hot enough to fuse hydrogen. For hundreds of thousands of years, it simply gathers material and grows warmer. A star still waiting to be born. Brown dwarf. Some clumps of gas never gather enough mass to ignite, and these are the brown dwarfs. They sit in a strange middle ground, larger than the biggest planets, but far smaller than a real star. Their cores grow warm enough to glow faintly, but the pressure inside is never great enough to sustain the fusion that powers true stars. Because of this, they are often called failed stars. They drift through the galaxy, slowly cooling and fading, giving off a dim, dull light that can be almost impossible to see. Red dwarf. The most common star in the entire universe is also one of the smallest. Red dwarfs burn their fuel slowly and carefully, using so little of it that they can shine for trillions of years, far longer than the current age of the cosmos. They are cool and faint compared with the sun, glowing a deep red, and not a single one can be seen from Earth without a telescope. The closest star to our own solar system, Proxima Centauri, is one of them. Quiet and long-lived, red dwarfs will still be burning long after brighter stars have died. Orange dwarf. Slightly larger and warmer than a red dwarf, the orange dwarf is one of the steadiest stars in the sky. These stars live for tens of billions of years, long enough for life to have every chance to develop on any world circling them. They give off a calm, even light, and rarely throw out the violent flares that trouble smaller stars. Many astronomers consider them the ideal place to search for life, more stable than our own sun and far more patient. Because of this balance, they are sometimes called Goldilocks stars. Yellow dwarf. This is the kind of star we know best, because our own sun is one. Yellow dwarfs are medium-sized, warm, and bright, burning steadily for around 10 billion years before their fuel begins to run out. Their surfaces reach thousands of degrees, and although they are often described as yellow, their true color is closer to white. They are powerful enough to warm the worlds around them, yet stable enough to hold that warmth steady for billions of years. Every sunrise, every season, and every living thing on Earth depends on the light of a star like this. Blue giant. Far larger and hotter than the sun, blue giants are among the most brilliant stars in the galaxy. They burn through their enormous supply of fuel at a furious pace, shining with a fierce blue-white light that can outshine thousands of ordinary stars. That brilliance comes at a cost, because a star burning this hard cannot last. Where a small star might live for trillions of years, a blue giant may survive only a few million. They live fast and burn bright, and their short lives almost always end in a violent explosion. Red giant. When a star like the sun finally runs low on fuel, it does not fade quietly. Instead, its outer layers swell outward and cool, growing to many times their original size and glowing a deep red. This is the red giant stage, and it is the future of our own sun billions of years from now. As it expands, it will swallow the innermost planets and scorch the ones beyond. A red giant marks the beginning of the end for a medium-sized star, a slow unraveling after billions of years of steady light. Red supergiant. Take the largest stars and let them age, and they become the true giants of the universe. Red supergiants are so vast that if one replaced the sun, it would swallow the orbits of the inner planets entirely. Betelgeuse, the bright red shoulder of the constellation Orion, is one of them, and it is close enough to study in detail. These stars are cool at the surface, but immense in size, and they are nearing the end of their lives. When a red supergiant finally collapses, it ends its life in one of the most powerful explosions in nature. Hypergiant. Beyond even the supergiants lie the hypergiants, the most massive and luminous stars known to exist. They are extraordinarily rare, and their power is immense, shining millions of times brighter than the sun. Such stars are deeply unstable, tearing away their own outer layers and flinging huge amounts of material into space as they struggle to hold themselves together. They cannot survive for long. In a matter of only a few million years, a hypergiant burns through its fuel and dies, often in an explosion far greater than an ordinary supernova. Wolf-Rayet star. Near the very end of its life, a massive star can become a Wolf-Rayet star, so hot and powerful that it blasts its outer layers away in fierce winds of gas, stripping itself down toward its bare, burning core. These stars are among the hottest known, surrounded by glowing shells of the material they have thrown off. They mark one of the final chapters a giant star passes through before the end. A Wolf-Rayet star sits on the edge of collapse, ready to explode at any moment. Variable star. Not every star shines with a steady light. Variable stars brighten and dim over hours, days, or months, pulsing like a slow heartbeat as their outer layers expand and contract. Some change because of activity within a single star, while others dim when a companion passes in front of them. One particular kind, the Cepheid, pulses with such reliable timing that astronomers use it to measure distances across space. By reading the rhythm of these stars, scientists mapped the true scale of the universe. A variable star is not broken or dying, it simply refuses to stay still. White dwarf. When a star like the Sun finally dies, it leaves something behind. The outer layers drift away into space, and what remains is the exposed core, packed into a body no larger than the Earth, yet nearly as heavy as the Sun. This is a white dwarf, and it no longer produces energy through fusion. It simply glows with leftover heat, cooling slowly over billions of years. A single spoonful of its material would weigh as much as a truck. Faint and dense, a white dwarf is the quiet ember of a star that has already burned out. Neutron star. When a massive star explodes, its core can be crushed into something far stranger than a white dwarf. A neutron star packs more mass than the Sun into a ball only a dozen or so kilometers wide, so dense that a single sugar cube of its material would weigh as much as a mountain. Many of them spin at incredible speeds, sweeping beams of radiation across space like a lighthouse. When those beams sweep past the Earth, we detect them as steady pulses, and call the star a pulsar. Few objects in the universe are as extreme. Magnetar. Among the neutron stars, there is a rare and violent kind. A magnetar carries the strongest magnetic field known anywhere in the universe, trillions of times more powerful than the field of the Earth. That field is so intense it can crack the star's surface, unleashing sudden bursts of X-rays and gamma rays that ripple across the galaxy. A single burst from a magnetar can release more energy in a fraction of a second than the Sun gives off in many thousands of years. Small, dense, and intensely magnetic, it is one of the most dangerous objects known. Black hole. For the very largest stars, death produces something that is no longer a star at all. When their cores collapse, nothing can stop the fall, and gravity crushes the matter into a single point of extraordinary density. Around it forms a black hole, a region where gravity grows so strong that not even light can escape. Anything that crosses its edge is gone from the universe forever. The star that once burned bright enough to light up a corner of the galaxy leaves behind only darkness and a pull that nothing can resist. This is the final fate of the greatest stars of all.